There are two apparently contradictory facts about the universe. Firstly, that it's expanding with acceleration in a spherical pattern around any observer, and secondly, that it is flat in geometric and energetic senses. No one really understands this. It doesn't actually make sense. So terms like dark energy and dark matter have emerged as ironic labels to buttonhole the unknown dynamics. A simple way of thinking about it is to suppose that the cosmos can be both spherically symmetrical and open or infinite, with increasing real distances defined on arc lengths of an open coordinate, by which I mean just a number line extending theoretically to infinity while also wrapped around an expanding spherical framework. You can structure a flat, as in Euclidean area law, on this kind of ever-increasing open coordinate. So as you move out along the coordinate, the area increases. In my last two seminars, I presented some overall ideas of where my research is going, to avoid getting bogged down in detail, and to show that it has some interesting endpoints and some fundamental principles behind it. In this seminar, I'm going to brave some of the detail. This diagram didn't quite make it into Seminar 1, but what it shows is the equidistant projection that emerges from the metric, and with it the general structure of this theoretical cosmology. The overall scale of the conformal universe is compared to the visible, which is the circle centered on C, as seen by any observer at O, via a light cone, the red spiral arc in the center. The blue volume shows the sense in which the gravitational potential and expansion kinetic energies in any spherical shell are equal and opposite at critical density. This diagram is based on the calculations, so it gives a good idea of the actual mathematics. In Seminar 2, I discussed a fundamental principle that could explain why this works. An interpretation of Huygens Principle combined in effect with Newton's first law to produce an Epstein diagram, which is a simple geometric construction of special relativity that is not part of the official canon of relativity, but remains a pedagogic myth, as the author L.C. Epstein labelled it. This diagram includes a foundation for the laws of optics, including relativity, and when you apply it as a Huygens expanding wave model, it leads to a four-dimensional cosmos with the correct cosmological redshift arising from the core differential equations of equal expansion and radiation that I relied on in Seminar 1. So this is clearly the foundation idea, and this is where I want to begin, to see how relativity comes out of a Huygens-Newton-Epstein diagram and what that implies in terms of the cosmos. What I'm aiming for is to contribute to arguably the most promising theoretical development in modern physics at the moment, the ADS-CFT correspondence, which is the unexpected exact agreement of conformal field theories, modern particle physics in other words, with a strangely inverted form of cosmology, the anti-de Sitter space. Willem de Sitter was the mathematician who worked with Albert Einstein to develop the first relativistic cosmologies, one of which is a hyperbolic inversion with some strange properties which we now know must work like a Minkowski spacetime projected as a hologram onto the perimeter of a 5D universe, like the surface of a black hole. And this is something like the universe we actually live in. The expectation is that we'll find a cosmology that fits the type of universe we see and has the right particle physics, but we're not there yet. I'd like to demonstrate a plausible approach to writing this correspondence by a reconstruction of special relativity, which is still the basic foundation of modern metrics in cosmology. I'm going to invert it from the hyperbolic non-Euclidean geometry of Minkowski spacetime, which is how it's written in the textbooks, to a simple Euclidean trigonometry as a new basis for the Lorentz transforms in a flat universe. I'll try again to demonstrate how this can be scaled up to a dynamic cosmology of the type I've been talking about, with an animated visualization as well as the words and pictures. So this is the online mathematics graphical software Desmos, and I'm just showing a conventional space-time diagram with space and time axes in light years. The red diagonal line is an ordinary Galilean trajectory with a linear function x equals vt, showing how far and in what time a high-energy particle jet can travel through interstellar space at a given velocity. We might imagine there's a solar sail spacecraft traveling with the jet, propelled by the energy of the jet. The orange dashed line is a light cone with the path of a representative photon or a signal from that distance, traveling at the speed of light, 1 light year per year. Particle jets can travel at any relative velocity up to just less than the speed of light, at which point they look and behave much like photons at a slope of 1 for 1. You can also see that the shortest time you can expect a return signal from some physical transmission like this is twice the light time at that distance, which is one of the few results where relativity actually agrees with common sense. I'll just set v back to 0.6. We're going to suppose that there are two parallel stars, H and G, separated by a local distance x. So these stars are stationary relative to each other, and that is the distance that observers near either star would measure. It's 10 light years in this case, but we can make that larger or smaller, and you can see that the representative photon always locates the trajectory in both time and space. So let's say there's a particle P leaving star H and arriving at G sometime later, something like 16 years later. The vertical distance shows how far light can travel in that time, while the horizontal distance is the fixed real distance to star G. We can use the light cone to work out when the home star H will see the particle arriving. If this was an actual relativistic jet hitting a star, it would do visible damage, stripping layers off the corona and producing light signatures that we would later see. Or the ship could send a signal that it has arrived. The particles in the jet would be relativistically dilated, probably outliving their half-life decay rates in a way that is calculated by the Lorentz-Doppler effect. This is something like the conventional Doppler effect or ambulance siren effect on steroids. A moving particle is literally time-dilated relative to us by the Lorentz effect, which has physical and geometric definitions for any relative velocity. The result, in any case, is that these high-energy particles evolve more slowly with extended half-lives, as is routinely confirmed by experiment. The proper time of a particle would work like the clock on board the spacecraft, which would show that less time has passed on the ship relative to the stationary observers at H or G. So I'm going to use an inverted form of special relativity to locate this dilated proper time in a flat Euclidean sense, so that the reduced time I'm indicating here is as shown to the correct scale. I'm also going to explore the equivalent contraction of space, where we know that the travel distance of the particle or spacecraft is less than the local distance. That is, the distance the particle travels is shorter than the true local distance. This is essential for the preservation of relativity for electromagnetic particles such as spacecraft, and it also preserves the most important metric properties. For instance, the same relative velocity is measured by any observer because the contracted distances and times have the same ratio, which is the velocity as obtained by local measurement. This slide is to show how standard model special relativity produces these effects. How we do it is we draw these hyperbolic time and space diameters that indicate the proper time and travel distance on the same axis and at the same scale as the local time and distance. So the local time and distance are dilated from the proper time and travel distance on the same axes and to the same scale. This shows an enormous amount of symmetry in the way space and time contract and dilate, with the important difference that the proper time is the time shown on board the ship, while the travel distance is the distance as seen when you look outside the ship's portholes. Everything that is not on board the ship is contracted in distance, while the traveller's proper time is dilated in the outside world. This is quite well explained by the properties of matter and energy. There's a light cone defining the center of these hyperbolic diameters, and there's a Minkowski space axis showing the effect that all this has on our definition of simultaneity, which is symmetric with the trajectory. So this is the Minkowski diagram, or it would be if this software allowed the Cartesian grid to follow the coordinate transforms, like this. When you do that, essentially by allowing the horizontals and verticals to follow the same angles as the space and time axes, then the diagram becomes non-Cartesian and non-Euclidean. You can indicate a length or an interval to scale in the depicted spacetime, but it's not to scale in a flat space, up to and including a cosmological space. So we can ask, is there a Euclidean form of special relativity, where the intervals can be seen to the correct scale and on the correct respective axes, with no distortions in the Cartesian grid? And would this be a special relativity that is consistent with a cosmologically spherical flat universe? It turns out that yes, there is, and it was first, to my knowledge, suggested by Louis Epstein around 1985. Epstein's method has just one assumption, that everything travels at the speed of light along its own unique world line. Relative velocities are projected trigonometrically into a stationary observer's reference frame, or parallel to it by a construction involving radiating light speed in all directions, forming these circles like concentric ripples. If I set the time back to 0 and let it run forward, you can see the ripples expanding more or less as Epstein intended. I don't know if anyone has made an animated version of Epstein's theory before, but it is very compelling. These new axes in green are the Epstein time and space axes, which are just the conventional Minkowski axes with contractions in the time and space directions. These are a particle's world line and the coordinates of all events simultaneous with the particle, consistent with Minkowski time and space axes, but in a canonical three-spherical spacetime with Euclidean geometry and ordinary right triangles. Conventional space-time intervals and relative velocities are both preserved, with contractions occurring to the correct scale along the Epstein axes. The two large semicircles represent the distance that light can travel in every direction from the origin in the proper time of the particle and in the local time of the observer. The two smaller semicircles are the same construction developed in terms of the travel distance, just the distance that the particle can travel at that velocity in the proper and local times. The ratio of a travel distance to a light distance, which is of v to the speed of light c, either as a ratio of these radii or as the opposite to the hypotenuse here, is a sine function of this angle phi in the corner of the Epstein axis, with a cosine that is exactly the Lorentz-Fitzgerald gamma factor. It's as though special relativistic contractions are trigonometric projections in a spacetime that is simply rotated to define the relative velocity. The proper time and travel distance are depicted to the same scale. When you draw a tangent to the light circle at the proper time, it intersects exactly with the dilated local time. If we highlight this segment in particular, we can see that it has the same length as the local distance. Again, you can test that analytically or just by drawing a circle of that length. Similarly, a tangent drawn to the local distance circle has the same length as the Minkowski interval to that distance. This is just indicating that the diagram is now Euclidean, with right angles and correctly scaled lengths that are depicted for both space and time. This diagram's getting a little complicated though. I'll just clean it up to show the main Euclidean results so we can see how that works when we adjust the velocity. Notice that there's a right triangle here and here, with the proper time and local distance as sides to the local time on the vertical, which is a hypotenuse. So that the Pythagorean sum inverts to the space-time interval t squared minus x squared as required, but you can actually see the intervals to the correct scale, and it is just the proper time interval at the particle's moving location. This succeeds in showing a hyperbolic relativistic geometry in terms of ordinary high school trigonometry, which is rather surprising. We can also show the proper and contracted lengths of any object, such as the size of an extended fleet between a starship and its leading probe, maybe 2 light years ahead of the ship in its own rest frame. That length is contracted in the reference frame of a stationary observer, as is the length of the ship itself. This works out by the same methods and shows most clearly the cosine effect of the Epstein angle phi. It helps to redraw the diagram with the moving observer's reference frame as the stationary reference frame, because if the observer's motion is inertial, neglecting gravitational effects for the time being, we should be able to define the system as though that observer is stationary and is the rest of the universe in motion relative to them. So here, the vertical axis is the world line of our particle P, and I've applied the same Epstein construction to the apparent motion of the other reference frames, that of the two stars H and G. So first we have to examine the motion of P relative to G and then apply that construction with additional contractions to the parallel motion of H and G. This is still a bit complicated, so let me show again the cleaned up version. So here the two trajectories going off to the left are H and G, with orange and purple Epstein axes showing that those two co-moving stars are also dilated into P's reference frame. The red trajectory going off to the right is still P, with green and blue Epstein trajectories indicating the dilation of P's proper time in those RFs, which are similar except that G sees P approaching and has an inverted relativistic Doppler effect. This is one of the most surprising results in special relativity, that each reference frame is dilated relative to the other, in almost defiance of common sense, and yet here in an Epstein diagram we can see it plotted to the correct scale by the same rules. To my knowledge, this is the only method in relativity that does this, and I really wonder why Epstein's method is not more well known. Notice the trajectory of G in motion towards P. The conventional trajectory starts from the contracted distance, which is the travel distance as measured by P, which must be consistent with that earlier result. The Epstein trajectory in purple runs straight through the local distance at the same time in H's reference frame, and that's simultaneous as far as the stationary observer is concerned, which is another intersection of these relativistic effects that I'm going to rely on for detecting any changes that might arise as we go to a larger scale, so keep your eye on that. So now I'm going to allow the particle's travel distance to increase with time, so we're no longer aiming for some particular galaxy G, but just travelling out into distant space at constant velocity. I'll just run the x slider forward in time as an increasing variable with all of the definitions that we've attached to that distance intact, and the first thing you notice is that the entire structure is self-similar, with the same angles and indeed all ratios of lengths maintained as the travel distance increases. This is only surprising because we've been playing with the velocity button so far, which does affect all the angles. Now we see that at constant velocity, the dynamic structure of space-time is geometrically proportional with passing time. The intersections of those trajectories that I highlighted remain simultaneous at the local distance of the stationary observer and the contracted travel distance of the moving observer. The other thing you might have noticed is that the relative timescale of this expansive process seems to decrease. It seems to slow down as time goes along. I'll just pause a moment and zoom back into the scale we had to start with, and if I set the initial distance to 0 and run it from there, the system at constant velocity seems to explode outwards at first, then decelerates, and if I zoom out to a larger scale, then the motion appears to be dilated. The velocity is actually constant. It's just a computerized parameter that increases at a constant rate as fast as we tell it to. But relative to the distance already traveled, the scale of the distance traveled in any interval decreases. Both these expansive effects, the similarity of scale and the decreasing relative scale of velocity, are characteristic of the expansion of the universe. The expansion law named after Edwin Hubble tells us two things. One, that the recession velocity of distant galaxies is proportional to distance, which preserves their relative distances as a system of fixed co-moving coordinates, and two, that the proportionality constant or Hubble value decreases with time. In fact, we can use the decreasing value of the recession proportionality as measured in the visible universe to calculate the age of the universe. The effects I've demonstrated here, I'll just assert as a working hypothesis, are a type of correspondence, a mathematical similarity in this modified Minkowski diagram to the overall behavior of a theoretical universe that it belongs to. It didn't have to be this way. Even without the relativistic effects, this apparently expanding diagram is not actually expanding, it's just proceeding at constant velocity, and yet it has the hallmarks of the expanding universe, as though simple kinematics are some important part of the physics underlying the expansion. To take the next step into a cosmological model, you might remember from those earlier seminars that I'm using an angular definition of co-moving coordinates. That is, the local distances you see here are projections of the Hubble radius or the size of the visible universe into observable local space by an internal angle, which I'm calling Q here for the Greek letter psi, in polar coordinates. In this setup, the co-moving coordinate is small, so the larger curvatures aren't visible on this scale, and you can see that it looks just like the special relativity model we've derived from Epstein's myth. But if I zoom out and then set the coordinate to increase, increasing the distance just as before but as a co-moving cosmological distance, you can see the large-scale curvatures, and you can see how the relativistic structure expands into that curvature. This is still the simple kinematic effect of increasing distances into the future from a fixed starting point, which produces a mathematical trace in the past of each actual observer. There are additional redshift effects that kick in as the universe grows in size. You can see how the light cone in yellow, indicating the information that a particle jet has passed some distance as seen by the home galaxy many years later, is arriving later and later because of the expanding scale factor as well as the increasing distance. The universe is much bigger at this later stage and is no longer self-similar in that respect, so later epochs are relatively distorted even at constant velocity. This is the cosmological redshift, and as I showed in Seminar 2, it works in this model pretty much exactly as in the standard model, with one minor correction that I'll demonstrate mathematically. These intersections and arc lengths are relative, that is, they all have relativistic metrics based on the same Epstein-Minkowski geometry, but with cosmological curvatures, and with an interesting divergence of intersections on the time axis into different points that depend on the scale factor, that is, the size of the universe. These second points, where Epstein first noticed these symmetries, resolves the geometry with these divergences relative to that point. In trying to locate that second point in the most general sense, I realized that the solution needs orthogonal directions at all points, like a circle, but the simplest and indeed first step I took towards that was just to locate the second point intersections using only special relativity. And incredibly, that turned out to produce two independent circles as exponential functions with two unique centers, much like a Doppler effect. Notice that the two past intersections I've highlighted are still simultaneous with the source galaxy, plus other points of intersection. This provides a simple calculation of redshift to examine how these effects explain peculiar velocities. The two co-moving galactic observers H and G independently observe redshift and blueshift with related Doppler, relativistic and cosmological scale components. The light cone introduces a Doppler shift with a scale factor, but the space axis introduces a second scale factor that intersects the Epstein world line. These combine as a Doppler index on the scale factor. The useful thing about this construction is that it provides a range of intersections with exact solutions, so you can determine lengths and times and angles along arc curvatures. We proceed by locating the particle's proper and contracted coordinates in terms of the physical angle of the particle at the present time, with rates of change determined by derivatives of the relative velocity defined in terms of angular velocities. The visible trajectory angle is found by considering P at an intersection of the light cone from H with the forward trajectory from S1. So we have past and future loci of the particle as seen from that earlier time S1 and the current moment SH, and that intersection defines the coordinate of the particle with a visible scale factor relative to the observer H, and A sub P, that's the scale factor of the particle. It's an exponential function of the particle's coordinate at that time. So this determines the visible coordinate as a function of universal time ratios and the peculiar velocity v. Since the time to H is the universal time at H, at the observer H, the time derivative can simplify, simply relying on some logarithmic definitions with t1 an initial constant. Working through that, we find that the initial time cancels, leaving us with a function of the Hubble constant at the present moment, inverted by a function of the Doppler effect. So HH is the Hubble value at H, here reduced by a form of inverse Doppler effect. The Doppler effect resolves completely with the physical angular velocity. If we substitute in for the inverse time, the angular velocity based upon the physical velocity, the speed of light, and the Hubble radius at that time, inverting the terms of this inverse Doppler effect, we find that that resolves simply as the rate of change of the physical angular coordinate reduced by an exact Doppler effect, so that the coordinate of the particle is simply the physical coordinate reduced by that Doppler effect. We can continue by locating the same intersection at the particle along the Epstein time and space axes, using the definitions of those axes along relativistically contracted lengths and the same definitions as before from the result along the conventional trajectory. We find that all of the key terms occur in the index of the exponential factor, which means that we can solve those index terms as a linear sum, which simplifies the result again down to the point where we can identify the contracted coordinate of the particle as a simple Lorentz contraction of the particle coordinate as it's seen in visible space. There are quite a few more mathematical proofs than I'm demonstrating here, but the result is that the physical Galilean and Epstein coordinates are all related by a relativistic Doppler effect, which seems quite plausible. So these results applied to the integrated proper interval along the Epstein axis produce an inverse relativistic Doppler effect in the index of the scale factor. If we take the gamma and the initial Hubble radius S1 as fixed values, they're constants, that simplification allows us to make substitutions for the rate of change of the contracted angular coordinate, leading to an expression for the total rate of change of the proper interval, that is the time experienced by a travelling particle relative to the time of the observer, which has the exponential function again, but with this inverted Doppler effect, inclusive of a Lorentz effect in the index. And we identify that with the scale factor. This actually reduces the scale of the present observer to the scale of the universe as it was seen at that past time, at that past coordinate. So the result is that we've got a reduced relativistic frequency which includes a Lorentz Doppler effect and an additional inverted Doppler effect in the index of the scale factor. And that's a significant new contribution to this cosmological theory. We can examine redshift and blueshift effects at the known scale factor of the early primordial universe based on the temperature at the recombination, the original temperature of ionized radiation in the Big Bang. And we can use this to estimate the underlying proper or peculiar velocity of our local galactic group, because the temperatures we observe are affected by our own proper motion. The standard model redshift uses the conventional Lorentz Doppler effect applied directly to the scale factor as though derived in a flat spacetime. The modified redshift model we've just derived, however, assumes the universe to be both flat and spherical, with a resulting small modification of the scale factor, raising it to a small positive power. Both forms of redshift can be applied to the temperature variation seen in the CMB, actually a tiny few thousandths of a degree variation around 2.725 Kelvin, which is the temperature of empty space plus or minus the temperature effect of our own motion. These temperatures correspond to frequency variations of the redshift, so if we assume a flat universe, we can solve directly for the velocity, which comes out at about 370 kilometers per second, a quite unreasonably large velocity for intergalactic motion, which most local studies put in the range of 10 to 100 kilometers per second maximum. But if we use the Epstein model, based on an assumed flat spherical universe, the presence of two independent Doppler effects means we can no longer solve the equation directly, but by an iterative technique or a Newton-Raphson method or just good old trial and error, we can find that the same frequency variation gives a much smaller peculiar velocity, about 50 kilometers per second, which is more or less right in the middle of the expected range. So this admittedly quite strange re-derivation of Minkowski spacetime into a Euclidean geometry with spherical large-scale symmetries based on Huygens Principle can be shown to produce the right Hubble factor, the right redshift and thermal age of the universe at the CMB, and a better interpretation of the CMB dipole that would agree with the results of galactic peculiar motion surveys. So I'm very pleased to present a possible resolution of this anomaly that has stood for the last 30 years. In my next seminar, next year probably, I plan to show how the same kind of refractive effects may alter the apparent motion of standard candles, producing the illusion of a cosmological acceleration, such as the high Z supernova surveys that are the basis for the current confounding of dark energy. If the wave theory foundations of this idea are correct, then the universal wave function should have a constant velocity with zero acceleration, which would have to revolutionize cosmology again if we can stand it. So I hope I'll see you then.